Okay, I guess we can start. So welcome everyone. And today we have our next seminar in the ITMP series. And our speaker today is Piotr Tourkine, and he will speak about scattering from production in 2 dimensions. Please start.
Okay, thank you very much. And thanks a lot for the opportunity to present this work that we've done in collaboration with Sasha Zhiboyedov. So I was asked to kind of include here and there bits of pedagogical material. So please bear with me if at some point I'm going through stuff that's like, you know, student level, but it's just for make sure everybody's on board. So just before I even start, let me present once, and then I'll present this over and over again to make this more precise. The idea behind this work that I'm going to present. It's so if you look at this, it's some kind of schematic version of the unitarity relation that relate the discontinuity of the amplitude to a sum over internal states, sum over 2 particle states and n particle states. And the idea of this title here is that by flipping this equal and plus sign here, you define this to be the scattering part. It involves only the 2 to 2 amplitude. And the idea is that we're going to be solving that object as a function of this object. So I'm going to make this more precise as we go on, and ask me questions at any time, please. So just a quick plan. I'll start with just the usual motivation of the problem. Then I'll present our numerical results, which are coming from 2 distinct schemes, one fixed point method and Newton's method. And then according to how much time there is, we'll discuss these things. So just start from the basic thing. We're going to be studying the S matrix, and that's the most basic observables of quantum field theories, one of the most basic observables of quantum field theories, and it describes how in states scatter to out states. We know how to compute the object for weakly coupled theories, and that's the sort of computation that are used at CERN daily, at one aspect of it. It's also used nowadays for gravitational wave physics, for instance. So that's a perturbative approach, and we're going to be taking a sort of non-perturbative approach here, which and one of these non-perturbative approaches is the idea of bootstrapping. Bootstrap, actually, I relearned that, I had forgotten, but bootstrap in English, that refers to this very small item here on shoes. I was kind of under the impression that it was more like an object that would go around the shoe, but anyway, it's something that helps you to put the shoe on. And the idea of bootstrapping is that instead of computing directly an object in a theory, you determine it by its symmetries. And I'm going to be talking about reviewing a bit of what people have been doing. And for instance, for the case of QCD, that's one possible approach, because it's strongly coupled. You cannot use perturbation theory, so you need to use different methods. And QCD, for instance, is one of the methods that is one of the theories that we hope are the numerical scheme we develop here should apply to in the future. So it was revived. So the CFT bootstrap, what's known nowadays as the CFT bootstrap, is something that was revived in that paper. And it was realized that it's an extremely efficient numerical method to compute, to determine the spectrum of CFTs, to determine CFTs in general. And it's just based on solving a simple constraint, which is a linear constraint, which is the constraint of crossing symmetry. So when you look at a 4-point correlation function in a CFT, it can be given by an expansion in both channels that are so-called S and T channels. And equating those 2 infinite series that involve the same coefficients give you a big matrix, which can allow you to essentially constrain your set of conformal field theories. Sorry, I forgot to define what CFT was. So that worked spectacularly well. That allowed to give some very nice about the Ising model, and it's still subject of loads of developments. And one of the reasons why it works so well is that it's a linear constraint. So it's not easy, but it's nice to implement. The S matrix on top of crossing, you want to solve for unitarity, which let's see. Maybe you could mute yourself. So unitarity is going to be a nonlinear constraint, making the problem much complicated to solve. And in the 50s, 60s until today, actually, people have been developing methods that could collectively be called as bootstrap, but are in general in the realm of non-perturbative method for the S matrix. And today, due to the recent spectacular progress of the bootstrap applied to CFTs, people have been trying to apply such numerical methods to quantum field theories. And our method that I'm going to expose is not per se a bootstrap thing. It's a method to construct S matrices. But I'll explain how it's kind of geared toward bootstrap. So just a few more basic words on S matrix unitarity. So it's just a statement that the S matrix is squares to 1. In terms of the T matrix, it gives this well-known expression. When you plug in 1 plus IT in the S squared equals 1, you get that you relate the imaginary part of the T matrix, the amplitude, to its square. But notice that there's a sum over this C index here. It's a sum over internal states, which is a complete set of states. And that sum covers a whole variety of objects. So it covers 2 particle states, 3 particle states, 3 particle states, and so on and so forth. Also, you have an integral over phase space. So the thing we're going to be looking at is the 2 to 2 S matrix or T matrix. And in that case, you could think of the labels A and B as being equal to 2 particle states. And in that case, for instance, you're summing over the N particle states. You still have the integral over phase space in there. So that should be well known to everyone. By the way, just one last thing, imaginary part is going to be the discontinuity of the amplitude. It's supposed to be understood as the discontinuity of the amplitude, the value just above the cut. This is to set notations. And in case this wasn't textbook material for you, this is just a graphical recap of this. This is the discontinuity. That's equal to the 2 to 2 part squared. And a priori, nothing that distinguishes these objects from this guy. It's just that actually it does. This is really the same guy here as it is here. And this is 2 to 3. So it's a structurally different object. And this is why you'll see later why we want to call all of these guys, we want to put them in here as a single guy. Okay, so this was to explain just the meaning of that graph we had on the introductory slide. Now let me get a bit more precise about what's happening. So the setup is we're going to be considering 2 to 2 scattering of lightest states in a gapped QFT. So we have in mind the standard Peskin and Schroeder type spectrum as it is here. You have an isolated pole, that's our lightest states. You have the branch cuts that starts at 4m squared. It's in red here on this plot below. And then we'll have bound states also somewhere here. And the goal is to construct functions that satisfy the S matrix axioms, unitarity, crossing, and some version of analyticity, which I'm going to make clear in case we study later. And the big problematic, the thing that this program tries to give an answer to, is that actually no such function was built as of today in more than 2 dimensions. We don't have even a numerical example, we don't have. And the thing that's particularly hard to enforce is this notion of elastic unitarity given crossing symmetry. And elastic unitarity, let me explain that in kind of 2 different manners. So let's look at this plot here. we have this branch cut that starts at 4m squared, or 2 if the 2 is inside the parenthesis, right? This is this guy. And if we have in mind, for instance, the pi-on-S matrix, the next multi-particle threshold is going to be at 4. It's going to involve a 4-particle state, so it's going to be 4m squared, which starts at 16m squared. It's in here. But in between 4m squared and 16m squared, there's not enough energy for these kind of guys to contribute to the discontinuity. So it's just really involving this guy. So the elastic unitarity is going to be the statement of unitarity in this region between 4 and 16. And it's actually a bit more, like a lot more subtle than just this, because, so first off, let me refer to this paper if you want a modern account of and some recent developments related to elastic unitarity. It's a very long subject, very old subject. So let's look at what's happening here. I'm just trying to give you a sort of account of the structure of elastic unitarity in 4 dimensions. So
sorry, are you looking at phi to the 4th theory specifically?
No. I said 16 because the pions are kind of phi to the 4, but it could be 9.
Okay, fair enough.
It could be 9 if you have a cubic interaction. Thanks. So on this plot, rho, this quantity rho, is the double discontinuity of the amplitude. It's the discontinuity in S and in T, where S and T are the usual Mandelstam invariant. S is the center of mass energy, T is the momentum transfer. You could think of these things as cuts of this 4-point function. And one of the statements of elastic unitarity is that the double discontinuity of the amplitude vanishes in this gray shaded area. Now we don't have just, sorry, this is rho on the ST plane. This part of the graph we've seen on the slide before, that part of the graph is the same, but for T, because the function is a function of S and T, and it's crossing symmetric. So whatever happens for S, it also happens for T. Sorry, just in case that wasn't clear, crossing symmetry is the statement that S and T can be interchanged. So this axis is reported on this axis, they are the same, and the elastic region for S is again that red quadrant. And the double disk is 0 under these two curves, which correspond to some different type of graphs, which would be, for instance, this graph or this graph, which each of these guys have a 4-particle cut in one direction, but a 2-particle cut only in the other direction. And this gives you these two curves. And the rho is non-zero in this gray area, green area here. And for elastic unitarity, in the elastic region, the statement is going to be that this guy, like I said before, vanishes. So it's in this region between 4 and 16, you only have the 2-to-2 amplitude that will contribute. And based on that seemingly elementary observation, you can derive a whole lot of very far-reaching consequences that are related to the fact that by crossing, you will be able to determine stuff that happen at very high, large T, to stuff that happen at low T, for instance, and that has lots of important implications. And again, I refer to this for more details on that. Oops. And amongst those two, amongst these relations, I just picked two to give some illustration. The first one, which is quite a powerful statement, is that X is known as X theorem. And it states that if you cannot have, as scattering implies production in more than 2 dimensions, which means you cannot have processes, amplitudes that do not have particle production. In other words, you cannot have in that sense, you cannot have the same phenomenon as you have for integrable theories in 2 dimensions, where you can have no particle production. And that one way to see that, which is a bit cheap, and it's explained in better details in here, but one way to see that is that scattering in the elastic region is this area here. And if you had no particle production, essentially you would expect your amplitude to kind of vanish here, sorry, your double disk. But by crossing, it's this red piece is related to the green piece here, and here that would correspond to particle production. So of course it's like a very quick explanation, and you need a few extra steps in between, but that's the essential idea. So that's one important consequence of this, and there's also something that's known as Grib of Ethereum, which I'm not going to talk about.
What's special about D equal 2?
Yeah, so I can't give you a full convincing answer because it's some stuff that my collaborators are more expert on. It's related to the inability to. It's related to the structure. You're scattering wave packets. And in 2 dimensions, there's something you cannot really do with these wave packets that you can do in higher dimensions. And it's kind of to do with the separation. If you have at least 2 spatial dimensions, you will always be able to separate your wave packets. And in 2 dimensions, there's a way you can just move them in one direction or the other. And that has to do with this effect, but I can't tell you more. We can discuss at the end if you want. Thanks for the question. Right, so there's this property of elastic unitarity that's really hard to enforce, and that has some impressive consequences. And as it seems to us, at least, there's just one scheme that was proposed in the literature to build an amplitude that satisfies elastic unitarity, and it was proposed by David Atkinson in the late 60s. So in that series of papers.
Excuse me, can I ask the following question? Is there some understanding that if you impose elastic unitarity, then the amplitude will be kind of unitary everywhere in the rest of the plane, or there is no such there's no such expectation?
No, I think you need to also enforce unitarity in the rest.
So this is the necessary condition, not the
right. Yeah, thanks. So just for reference, that's the series of papers in which Atkinson worked out the stuff that we're going to be building on. Notice the typo in his name for the first paper, and if you're interested, maybe that set of lecture notes is a bit easier to attack, because those papers present actually quite dense mathematical proofs, which I'm going to review shortly afterwards. Okay, so the essence of the Atkinson program, as we see it, at least, he may have had maybe a bit more focus on the iterative structure. But the way we want to solve it and we want to use it is as following: is to recast the unitarity relations by flipping this equal and plus here, and by treating that guy as the input and this guy as the output. We want to input a function that takes into account that term. In practice, we're just going to ask that this function vanishes below 16 m squared. And we want to solve that as a function of this guy. So we'll discuss the implication of this in the next few slides. So if you still have questions by this time, do ask me. So, because you may be wondering about it creates a huge degree of indeterminacy. You seem like you'll be solving the problem by assuming something that's even bigger than the problem itself, and we're going to be discussing this and to what extent that's justified or not. So what Atkinson did in this series of papers was to provide some mathematical proofs of existence of of functions that satisfy crossing, unitarity, and Malasham analyticity in 4 dimensions. That's the sort of precise punchline. So at least you know these functions exist, which otherwise we know kind of QFT. Actually, they didn't even know if QFT worked or not by then, but so we know these functions exist. And to explain it again, to explain how we proceeded in like 2 slides, we're gonna be looking at the double disk of the amplitude. Again, rho is the disk in S and T of the amplitude. And the way he proceeded was by seeing the unitarity equations as the fixed point of the map that's given here. Rho star equals phi of rho star, where phi of rho is just the right-hand side of the unitarity equations. So in terms of these little drawings we had before, it's this double green drawing and the double yellow guy, which correspond to essentially rho squared, like it's obvious, and a function which instead of calling sum of blah, 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 we just call a single function of S and T. That's called V in L for inelastic. And he applied fixed point theorems, more precisely this Luray-Schauder principle and contraction mapping principle, to the sequence where you define the next step by the right-hand side of the step before. And he could show that this converges to a unique solution for some starting point, for some range of starting points and inelastic function. And just to be more clear, you define the imaginary part at step n+1 by the function you get at step n. This you don't iterate, it doesn't change. Sorry, there's n's everywhere. This is the thing that changes. And with this step n+1, you plug it in here and you go on. And what it will show is that this map has the suitable properties to give you a solution. And that's
can I ask a short question at this point?
Yeah.
In general, perturbation theory is not convergent. So if you literally compute all these diagrams and sum them up, then we're not going to get any nice function satisfying all these conditions. So how this complies with his proof that seems to be using the same kind of diagrammatic expansion?
Thanks. So there's a really great question. There's 2 aspects of it, and I'm gonna kind of discuss them again later, but let me answer now anyway. Firstly, you remarked that this guy, you're not iterating. So by doing this iterative procedure, you're actually building, if you call this guy with a black dot and this guy with a yellow dot, you're actually building a kind of bead of things with black and green that are in arbitrary positions. I'm just drawing a quick example. That's the kind of diagram you're generating if you want, if you just look at this. And the diagrammatics of that is not the same as the diagrammatics of Feynman diagrams, which usually give you factorial divergence and this Borel singularities, etc. So firstly, in terms of graphs, that's not exactly as bad as summing Feynman graphs. And it's actually the number of graphs here, you can compute that it's just, it can converge. And the second point is still, if you plug for this guy, if you're good enough to compute that guy, you should be reproducing exactly perturbation theory. And in that case, indeed, if you actually, it's an even more a stronger version of this. If you plug any fixed order recent perturbation, sorry, not recent, any perturbation theory at fixed order for this guy, you can show that there's a version of this thing that I called Grib of Ethereum before that will tell you that it cannot converge. So it's something that Atkinson didn't do, but essentially, if we follow the reasoning you just explained, you should land in a region of function space that Atkinson would have excluded by its convergence proof. Atkinson proved that in some range it converges, and by doing what you're suggesting, which is very the natural thing to do, you plug in here perturbation theory at fixed order, you will have a map that diverges, so it will not work. So the third point of the answer is that if you want to plug perturbation, something that resembles perturbation theory here, it better have some notion of how you resummed it. So, so in a sense, playing with that function, not wondering about Borel resummation or anything, you just plug in a function that works. It gives you a way to bypass completely that problematic. I'm happy, if that wasn't clear, we can discuss it again at the end, and I'm going to be mentioning some related things related to this again, but thanks a lot for the question.
Yeah, many thanks.
I wanted to ask another thing. So,
yeah.
So as I understand, you can put, so as an input, you use some yellow thing, right? And then for this yellow thing, you generate a solution, which is green thing, right?
Yeah.
And how rich is the space of acceptable, let's say, admissible yellow inputs?
Right. So essentially, it's infinite. So what Atkinson, in terms of the mathematical, mathematical proof, Atkinson constrains. He says that, okay, let's not look at this. It's like mathematical stuff, but he says that if you have your function v in some suitable ball in function space, for any function v in this ball in function space, you will converge. If the inelasticity becomes too big, actually, yeah, it's at least something that we observe very clearly experimentally, like numerically, and we actually understand why. If this inelasticity becomes too big, you don't have convergence. So, but the idea is that it still covers the whole of function space, sorry, S matrix space.
You say basically that there is no constraints on this yellow part, except that it should be not too large in some sense.
No, I mean there is constraints in the sense that it cannot be too big, and it probably cannot grow too fast, and there are a variety of constraints. It cannot be anything, and whatever it is, it needs to correspond to a physical. So there needs to be an S matrix that is compatible with it. So whatever constraints you have on S matrices, it will apply to this yellow thing.
So you mean, for example, you don't insist on any analyticity properties, or you impose?
No, sorry, of course they will have, sorry, they have very clear analytic properties. That guy, we're gonna take that it vanishes before 16m squared. And at 16m squared, it can do, you know, it can live its life or go to a constant or grow like S. But it cannot, it's not nothing. It's something that has the
real axis, it could be anything, right? Starting from
yeah, I mean, pretty much. You want it to have some reasonable convergent, some reasonable behavior at infinity. Like otherwise, you need to do subtraction, etc.
Isn't it possible that you design some, you know, function of the real axis such that it has physical poles somewhere in the complex plane?
Yeah, you could add a function that has, so yeah, you specify the function only on the real axis. That in two dimensions, what we observed, I cannot tell you for 4 dimensions. In 2 dimensions, what we observe is that the only thing that this guy is gonna do is gonna change the zeros of the S matrix in the first sheet. This is the only thing that this guy is going to do. Change the zeros of the S matrix in the first sheet between 0 and 4m squared. In 4 dimensions, I'm not sure. Okay, so that's a bit kind of recap. That's related to the questions that were asked just now. Firstly, let me re-emphasize this comment. We don't choose all of these guys one by one. We pick up a big function that takes into account all of them. And in 2 dimensions, it's going to depend just on S. We believe that the problem is complete in the sense that because we have this freedom to choose anything we want here, we should be able to describe all the actual physical amplitudes. And consequently, the philosophy is kind of geared towards Bootstrap, because by playing with this function vi, you explore the whole set of function space, which is what the sort of games you want to play with Bootstrap. Okay. So now I'm gonna go to more details about 1+1. So if there are other questions or if my answers were not convincing, please, I'm happy to continue the discussion now. Okay, so let's go to 2 dimensions. So why did we do 2 dimensions? Because we want to do 4 dimensions, and 2 dimensions is like a case where everything is under control. S matrices are explicitly known for integrable models. The kinematics is much simpler. It's just one kinematic invariant, S, instead of S and T. So it makes complete sense to try the ideas in 2 dimensions and see if the numerics can work there. So like I said, T0, so that's out of the game, and crossing is just going to be related S and 4 minus S, 4m squared minus S. Sometimes I'm just going to be assuming that m squared equals 1. So the analytic properties of the S matrix we're studying are as follows. There's the cut from 4 to infinity, and the cross cuts from 0 to minus infinity. And then we're going to have these bound states at mp squared, like m pole, that are connected by crossing to 4 minus mp squared. For those S matrices, elastic unitarity is the statement that S is exactly a phase between 4 and S0. So what I call S0 here, I was calling 16m squared before. It turns out it can be actually whatever number. It doesn't matter for the numerics. It's all the same. So let's just keep S0 for now. In elastic unitarity, the S matrix, other channels open past S0, and the S matrix is not just a phase anymore. And one way, and crossing is just that S of S is S of 4 minus S. One way to encompass these 2 versions of unitarity is to introduce a function f. That's going to be the yellow thing. So S vanishes below S0, and above S0 it can be, let me draw that in yellow. It will be something that, you know, does whatever it wants. In practice, for us, yeah, let me tell you after, because I don't know for F, I know for V. So that's the setup. In terms of, we worked at the level of the amplitude, T actually. So in 2 dimensions, T is related to S with an inverse look, with this inverse factor that may be slightly odd to you. Let me just, it's just coming from kinematics. The idea is that as operators, S is the operator 1 plus I times T, or amplitude T. And this operator, and this has a delta 2. It's a delta function of the 2 vectors. The operator 1 is a product of delta functions. And when you want to put the 1 in factor here, you have a Jacobian that comes from relating these 2 delta functions. And that Jacobian is essentially this term. So that's why there is this factor here, just to clarify notations. And now here is the yellow thing. This V in L is going to be our input. And so it's related to this F by just this factor, this square root. And that's the unitarity relations that we're going to be solving numerically. And the problem, just to state it in boldface almost, the problem is the following. Given this V in L, the yellow thing, find an amplitude that satisfies, sorry, in 2D, we don't need that, that satisfies analyticity, so the cuts, like I said, crossing and unitarity. And we will solve numerically in 2 different ways. First one is going to be to find the fixed point of this map phi, where phi of int is given by this, and at the fixed point, phi of int is equal to int. So you have found an amplitude that satisfies unitarity. And we're also going to be doing Newton methods, but I'm going to just explain. It's going to be the same idea. I'll explain it after exactly why we do this. And if you paid attention, the way I write this map here is kind of odd. I'm referring to this little box. Phi contains a step by which from int you reconstruct the real part so as to create this. So you have a dispersion integral in the business. And at every step, this gives you in t at n+1, then you need to reconstruct the real part of t from in t by doing a dispersion integral. And that's using this kind of identities. So derivation should be standard. Let me just quickly explain it again. By looking at the integral of t around a small contour, t over s minus w, you get t of s, and then you deform the contour everywhere where possible. The arc at infinity drops. You remain with some integral along the cuts and around the poles. Standard stuff. Along the cuts, you relate the part. You relate the imaginary part above and below. There's a minus sign, so you get the discontinuity, which is in. You get these guys, which are the integrals along the poles. And that's about it. You also get a constant if t goes to a constant at infinity. That's the class of amplitudes we study. At worst, t of s goes to a constant when s goes to infinity. You could have done t of s grows like s to some power. Then you need to do subtractions. The same idea work, but it's a bit more involved because you have to deal with these subtraction terms. So let's not look at these guys. This is the setup we work on. So this is how from the imaginary part, you reconstruct the real part or the function itself. Then you can take the modulus squared. So notice also that it's important for the numerics. You only need to know, sorry, I forgot to explain. Here you have two terms. This guy comes from the crossed channel. So you only need to know the values of the function int on this axis for infinity, that's all. And with this, you reconstruct the value of t on the same axis and you go on. So you want to know the value of int on that axis. That's enough information.
So in some sense, you also have include information about bound states here.
Say it again.
Do you also need some information about bound states?
Yes, exactly. We will be fixing the bound states. Yeah, I'm going to come to this. And that's a technical detail.
Sorry, so
but
MP here is the bound state mess, right?
Yes. Yeah. That's going to be an input. MP squared is the bound state.
And you don't allow several bound states. You just allow one.
No. We also worked with many bound states. It works as well. For the sake of the example, I'm showing with one bound state, but we also implement it for many.
Okay.
Thanks. So one problem is that if you just write the dispersion relation like this, though before I was writing t, and now I'm writing the real part explicitly, so that's a principal value integral. It's just the same thing. The problem is that at 4m squared, written as it is, that object does not vanish. And that's a problem because it creates then an object, it creates int at n+1, which will blow up around 4 because of this inverse factor. If the real part at step n does not vanish near 4, it means that the imaginary part at step n+1 will diverge at 4. And that's messy because then you plug n+1 here, it creates a divergence. You don't want this. And moreover, you know that, let's not look at this. You know that non-perturbatively, the amplitude, you can extract this very easily from the unitarity relation. The amplitude needs to go to 0 when s goes to 4. So you can enforce this condition by hand. You demand that the real part is 0, and you could do this by tuning either of these two parameters. We decided to keep this guy fixed, which means that the value of G, which before I was writing like you could choose whatever you want. No, you cannot choose whatever you want. The value of G is determined by the fact that this whole thing, when S equals 4, is equal to 0. So the iterative map gives you int n plus 1 as a function of int n, and g n plus 1 as a function as the same thing. If you didn't follow that, never mind. The idea is just that you also need to iterate the coupling of the bound state, but it's just a detail. Let's focus. Let's recap the inputs. The input.
If you have several bound states, then you impose also some residue. Yeah. You choose some residues, and together with C.
Good point. Yeah, if you have many bound states, you fix the coupling for bound state number 2, blah, 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 bound state number n, if you have n bound states, and for bound state number 1, you do this recursion. But these guys you would consider as fixed as well.
Okay.
Does this mean that one of the residuals is, it cannot be fixed by hand? This means that for different functions in the right-hand side, the yellow ones, you can obtain given masses, you will obtain a set of values of this residual, right?
Yes,
and
correct.
You can say that it cannot be equal to, like, I don't know, 3, right?
Correct.
Is that correct? Okay.
Yeah. It's exactly the thing we're doing. I'm gonna show you. I have some plots on this after. Okay, so that was for the explanation of the problem.
One more question.
Yeah.
You also choose arbitrarily your masses of the bound states?
Yes.
Or they are determined by some, something.
You fix them by hand. It's not determined by what's gonna come out. What's going to be determined are the zeros of this matrix, but the poles you need to fix by hand with this procedure.
Okay.
So it turns out that this problem actually has an analytic solution. So just to make sure you don't spend time wondering about if I just said what I actually said, the problem is solved analytically. And we're going to be developing a numerical scheme to solve that solved problem. But this is important to us because it gives us a way to understand how to proceed in higher dimensions afterwards. And that was actually already resolved by these guys. So like we're resolving. And I'm going to be comparing to this paper, which I'm going to refer to as PPTVRV for these authors. And the question I was just asked before about the coupling is actually answered also on this plot. This is the plot that shows analytic and their numerics for the problem. So now M1 is what I was calling MP on the plot before, and that's the coupling G in logarithm. So what they observed is that, and what they a posteriori discovered, it was already known, is that not all couplings are possible, and there is a value of the coupling that is maximal given some MP squared. If the maximum value would be given by whatever number is here, and that follows this curve. If you ask the question, is there?
I didn't get that.
Sorry.
Could you try again?
No, Siri is just sorry. Siri is thinking I'm talking to her. If you ask the question, is there a theory that has coupling this and bound state here? The answer is no. So let me present this analytic solution. Good. Let me present how to solve this problem analytically. So here, Fi is the yellow thing that we were talking about before. it enters, so S of S, sorry, I was confused by my iPad just now. S of S is the solution to the problems I was stating before. So you have this F function that you want and you want crossing and inelasticity, etc. F enters just in this exponential. This guy I'm coming to in a second. And that's the exponential of this integral. And in here, S elastic is just defined by any function of S that's modulus 1 for S bigger than 4 on the axis. Of course, that introduces some ambiguity because there's many functions that do this.
Sorry, the left-hand side here is what? S of S.
Yeah, I explained poorly, sorry. S of S is the solution to, where is it? To this. S of S is the solution to this. So it's a S matrix that is 1 between 4 and 16. It's smaller than 1, and it's smaller than 1 in a way that's given by this function F. And it satisfies crossing.
Okay.
Thanks. Come back. Okay. But it's the only thing is that this function here is not constrained. It can be anything. It's actually slightly constrained because if you fix the bound states, this will have to be in there. But let me describe it a bit more precisely. And just a comment before I describe more of this S elastic, that type of ambiguity you don't expect in 4 dimensions because of Axe theorem that prevents to have integrable type or theories that are S matrices that are phases everywhere and that are non-trivial. So that's something that we had to deal with in this problem in 2 dimensions, but it shouldn't be there in 4 dimensions. So what are these elastic S matrices? So first, they're pure phases, so they have no particle production, and they typically they correspond to theories that are called integrable theories. And there's huge literature on this, obviously, but maybe the review by Patrick Dore is a good starting point if you're want to think about this. And they're actually known explicitly. They're spanned by the set of what's called CDD, Castillejo-Daritz-Dyson S matrices. So a CDD S matrix is a function of S and M0, where according on the sign you choose, M0 is going to be a pole or a 0. If you choose the plus sign, you see that when S goes to M0, you have a pole in the denominator. And in that case, M0 would be the location of the bound state. And if you choose the other sign, your S matrix has a 0. And the statement is that any S elastic is a product of these guys, and that's it. That's all you can have. And you can prove this. It's not actually hard. It requires using that this maps you to the unit circle. But I don't want to explain this unless you have questions. Let me please trust me on this. So again, S elastic is a product of these objects. And it's up to you to choose what this mi end up signs, plus and minus. And that's a turbo plot. This is what they kind of look like. If you take one factor, so that would be the S matrix SCDD of S and a pole at MP here. And in terms of T, this function T, the real part goes to a constant when S goes to infinity. That's S here. And the imaginary part is 0 before 4, and then it just lives its life. It goes to 0 in that case.
Excuse me, is it a S matrix of an arbitrary integrable theory?
Yes, sorry, I should. I think so. That's out of my domain of expertise, but they are this guy in particular, I think is the S matrix of the lightest breather in some Sine-Gordon model. So those guys you can find appearing easily in Sine-Gordon. And I think the statement would be that any integrable model needs to be, the S matrix of it should be given by some product of these guys.
Yeah, so my question is, you have a non-integrable model, so you have S elastic in front of your formula. So
yes.
Can you say that your S matrix is S elastic in front of the formula should be also of this form or no?
So, right, thanks. Yeah, good question. So what's going to happen? Actually, maybe I am actually discussing this in a few slides. Let me see.
Okay, sorry, I will go. Wait.
No, it's yeah, I'm going to be explaining this over the next slides, and if I haven't, please ask me again. So, right, so this is just to give you an example of what these objects look like. And I wanted to write, so for a given set of poles at locations M, P, J, and zeros at locations M, Z, J's, the constant at infinity, it's easy to compute. It's given by this sum. Don't look at too much of the details, but the idea is that even at fixed pole locations, which is our case, many amplitudes can have the same C infinity by either adjusting the number of zeros, so you could add more zeros to match, you know, you want to fix C infinity and you demand, is that enough to fix my amplitude? You fix C infinity on the poles, is that enough to fix S elastic? No, it's not, because the zeros, they can arrange themselves and move a little bit to make this total contribution adjust and be invariant. You could also change the number of zeros. So fixing the poles and C infinity is still not enough to fix S elastic, because you have this zero factor, and they can contribute in different ways. Just one remark, they decrease the constant at infinity, and we may use this later because of this sign. Have I actually answered your question? Sorry, what was the question again? I'm not sure I answered it now, actually.
So the question is that, yeah, so the S matrix of an integrable theory has this form. So should we expect that the S matrix of your non-integrable theory,
yeah,
part of this
right,
matrix has this form as well?
Yes. Thanks. So let me just recap this here. So the analytic solution is S equals S elastic times this exponential log of 1 minus F, etc.
Mm-hmm.
So here we will fix, this is fixed, given.
Mm-hmm.
Oh, by the way, we're going to be also, this is going to work when you fix to 0, F. Mm-hmm. Whoops. Come back. This has disappeared, damn it, sorry. So I explained to you how this integral is given. Here we're going to fix the bound states. And what we're going to find as the output is the zeros. So given F, you're going to find different factors for the zeros. And we're also going to find this coupling G. So this is not going to be fixed. The zeros of S elastic are going to depend on this F here.
But S elastic is not the arbitrary function of this model. No,
it's not.
One, no?
No, it's not. It's not.
Okay. Mm-hmm. Okay.
You know, when you run
the form of the integrable S matrix, right?
Sorry?
Its form is different from the integrable form that you just showed us.
No. When we will run the algorithm with a given F, we're going to find explicitly an S elastic that is going to be a product of these objects I showed you before.
Okay.
The bound states are going to be there. And then what's the unknown is going to be where are the zeros exactly, and how many zeros are there. And that's going to come from the algorithm.
So basically, the explicit formula that you have shown for the solution is actually not yet a solution, right? This elastic S is by itself dependent on your choice of F, right?
Okay, I'm sorry, I explained myself poorly.
Okay, if you go back to the solution, explicit form of the solution, right?
Yeah.
Which you showed schematically here in this plot. In this, yeah, okay, here. Good. Yes. It's
I'm sorry,
it's not yet an explicit solution, right? Because this elastic part in front depends on the function F. Is it? Does it?
Okay, so this, okay, just yes and no. So what's gonna so that's a solution to the generic problem, and in our problem specific, we're gonna fix the constant at infinity and the bound states. This can have any constant at infinity and any bound states. We're gonna fix that, and given that this is fixed, F contributes to the constant at infinity, so it impacts where the zeros can be.
So in the general solution, this S elastic can be anything, right? Is that correct?
Yes, right. Yeah. But for our problem, where we're gonna fix extra stuff, S elastic is gonna be constrained by this extra stuff.
Okay, I see, understand.
Thanks. Okay, so let me present. If I understand correctly, I have something like 15 to 20 minutes. Is that correct?
Yeah, we have many questions, so I think like 15 minutes you have at least.
Thanks. So now is our numerical results, and maybe I'm just gonna be just spend more time on this than the other. As a comments, we did everything in Mathematica so far, and we're currently using more powerful methods to solve the higher dimensional question. So just a few steps to make this thing numerics. Remember, we want to know, make this thing numerical. You want to know the value of the function on this axis, so you discretize it. Before discretizing, you map this to 0, 1 by inverting S. So you want to know the function, the values of a function between 0 and 1. So you discretize on a grid. You discretize this function on a grid, x0 equals 0 to x capital N equals 1. The object we're trying to solve is the imaginary part of T. Now I call that guy rho. So please don't be confused. It's not the double disk. Now whatever you see rho, it's IM, single disk. And we did two different type of interpolation. We did linear spline interpolation. So the function is just a straight line between different successive values of the function in blue. So the linear interpolant is this red curve. Rho I is the value of rho rho of at point xi. So now we discretized our problem. We want to know the set of these rho i's. We have capital N plus 1 variables that we want to determine. And in theory, I'm just going to give you a bit more detail, but it's just about now inputting that straight line function, piecewise linear function in the equations I've given you before, treating that object as a vector and iterating the map acting on this vector. And that, so let me give you just a bit more details on this. Whatever interpolation type you use, polynomial interpolation or this piecewise stuff, you end up with a discrete version of the dispersion integral. It's pretty easy to see because the thing between 0 and 1 in the inverse variable, or 4 and infinity, breaks up into elementary integral between these successive points. And that object depends on rho I and rho I minus 1. And that's it. So if you take this sum and you express everything, you can re-express everything as a matrix acting on the row. Because the next guy depends on row I plus 1 and row I. And the coefficient j, the coefficient of row j, is just the sum of these two coefficients. And you go on like this. So you construct this matrix B here, which is just giving you the exact dispersion integral on the red curve here. So it's the exact dispersion integral on the approximate function. And that was important for us to be able to compute this guy in advance, because then you don't have to compute dispersion integral at every step and you're just multiplying matrices. You can be really fast. So fixed points, let me just remind you quickly what this is about. You want to find x star equals f of x star. That's this point here, where the blue curve f touches the diagonal. You start from a random guess, x0. You look at f of x0. This is x, you call that x1. It's here. And by playing this game, you realize that you're actually building this little staircase that drives you towards the fixed points in general. I had some anecdote on the Babylonians, but I'm skipping this in view of time. So you just want to do this for higher dimensions. Now, again, you're having row n. So now I have another index, n and j. N is just the iteration counter, and j was the value of the function at xj. You have this row nj's. You want to find row n plus 1 I. And it's given in this form. It's given by this form. That's just a discretized version of the map. This is the modulus of the amplitude squared, which is given by the imaginary part squared plus the real part squared. And the real part, if you remember, it's just given by this dispersion integral plus the pole terms. I told you how the dispersion integral gets discretized by B acting on the vectors of rho. And that overall results in this rather simple object, which is just a matrix. It's a different matrix because it contains the poles as well, etc., acting on rho, and a vector that also contains the poles and the constant at infinity. Let me just not give you too much detail. You've seen the continuous version. This is the same as the continuous version, but applied on this function that's piecewise linear, and hence depends only on the values rho I. It's exactly the same. And it's a quadratic map. You have rho at step n plus 1 is something like rho dot a dot rho plus b rho plus c at step n. Kind of something like this. So this is, you have this vector of rows, and this is what you want to iterate. Let me just make a comment. In general, we want to find the solutions of this equation, but we don't, I've explained you how to do with the, I've detailed you a scheme that uses this iteration. In general, you don't need this n here. Let me remove that in red. What you want to solve are the values of a function rho I that satisfy this. Any method that gives you a way to solve this system of capital N coupled quadratic equations, any method that gives you a solution to this is good. Fixed point is the basic thing. You apply the map over and over. But we also did Newton method that ended up being more powerful than fixed point. Fixed point is what Atkinson suggested. So we ended up doing Newton method, which was more powerful than fixed point. You could come up with a machine learning solver for this. It would also give you a solution. So any method that works is good. For us, what took the longest to compute was this guy, but you compute it once and for all. And then you can just run the algorithm over and over again. And the map defined as it is, it encodes everything, unitarity, analyticity, and crossing. You don't need to input crossing at the end or something. That's just it. You don't want to solve the solution for this capital N rho I variables. Everything else is given. So that's for the numerics. Now let's go back to this, to the fixed point. Yeah, and recap. Again, the inputs are as follows. I'm presenting you for one bound state at MP, but we played for many. The input is the constant at infinity, the V in L, and the location of the bound state. The output is the S matrix. So what S matrix does it give? We observed that it converges with one pole, it converges systematically to an amplitude with 1, 0. You could have had more zeros, and I'm showing you an example, but it doesn't converge to the more zero case. It converges only to the 1, 0 case, interestingly. And it's kind of independent on the starting points. Here, hopefully there's some animation that should run. And the convergence stops when the constant at infinity or the inelasticity becomes too big. And now that's annoying. Let me show you here. So it's like the example of how this object works. You start on the blue curve and rather quickly it just collapses on this black curve, which is the explicit solution. And notice that, sorry, there's no inelasticity here. We solve for f equals 0. So you start with a random guess, like this sine object here. And after like 5, 10 iterations, it just collapses nicely on the thing. So again, what I'm showing you here doesn't have inelasticity, but it's not important for us. It has inelasticity given by 0. Okay, now it works. Who knows? And a few words about the convergence. It's easy to understand in 1 dimensions, and then in n dimensions, it's just a generalization. It converges when the value of the derivative of the function at the fixed point is smaller than 1. When it's bigger than 1, like in this case, however close you start from, it repels away from the fixed points. And in n dimensions, it turns out there's a very similar arguments, which is instead of using the derivative of the function, you use the spectral radius of the Jacobian. Jacobian is just the derivative of the map. And the spectral radius is the largest eigenvalue. So whenever the largest eigenvalue is smaller than 1 at the fixed point, you converge. So that gave us a criterion to understand when we converge or not. It kind of goes beyond Atkinson, by the way, in that case. Just a quick comment, because now I don't want to spend too much time on this anymore, to show you what's happening. Those amplitudes are CDD factors with the same bound states, but different number of zeros that nevertheless have the same constant at infinity. They end up on the same point here. Remember that 0 is mapped to infinity for S. So the real part goes to the same constant. They have the same bound states and they have the same inelasticity, which is 0. So in practice, they're both equally admissible solutions of the problem that we ask. And now we want to know, how does the algorithm choose to what it converges to? And well, you just look at this, the eigenvalues of the Jacobian. For the 1, 0 case, all the eigenvalues are nicely contained in 1. For the 3, 0 case, so this yellow curve, the eigenvalues wander all over the place. And let's see what happens. You would expect then that you had some divergence, and indeed you have divergence. When you start on top of the solution, so here you're going to be looking at the blue curve on top of the solution dashed black curve. And now this is annoying. You'll see that after a few, so here you see n is changing, hopefully 4, 5. It kind of stays on top, but after like 8, 10, it starts to go all over and it eventually diverges completely. So how does the algorithm know to where to converge to? Well, it simply doesn't converge for this case. And now, if you remember this plot I showed you before, that's our results on top of this plot. We converge to practically all of the function space apart from a gray band in which the algorithm doesn't converge. Whenever we had n pole, we converged to n0 amplitudes, and the m01 no. Yeah, and I'm gonna switch almost directly to the results of Newton's method, just explaining it in one dimension first in 1 second. Now we want to find, with Newton's method, you want to find the roots of a function. So the point where the function is 0 here, x star. And the function you look for the root is this guy, g, defined by x minus f of x. So when you have a root of g, you have a fixed point of f. And we're looking for fixed point of the unitarity equations. So this is what we're going to use and apply Newton methods to. And remark, it uses an inverse derivative here, and that's what makes you go faster, because the slope tells you where to go and you converge much faster. Not much detail. Essentially, you're doing the same thing, and there's a way to understand also the convergence in terms of the Jacobian, but not this time, not because it's bigger than 1, but because it touches 0. When the Jacobian becomes singular, because you take the inverse, you have you don't converge anymore. And with this, we were able to extend a bit more, to find more amplitudes and cover almost all of parameter space, but not completely. And we found some cool behavior, because now the problem I was telling you before, if you followed me, I was a bit quick, on the 1,0 versus 3,0, and that they are both admissible solutions. Now the Newton method can distinguish and can converge to either of these. And the way it decides to which amplitude it converges to depends on where you start from. And that's easy to understand if you look again at 1 dimensions. And after this, I'll be done, so bear with me for another minute. You look for the roots of the polynomial z cubed minus 1. They're just given by 1, 1, and these 2 complex numbers here and there. These 3 roots. You look for them using applying the Newton method. So we're going to look at the graph on the left side here. The blue region is if you start in the blue region anywhere, you're going to converge to the root at 1, to the root of phase 0. But it's also true for these blue regions here, there, etc. So likewise, if you start in the green region, you'll end up at the roots of phase 2 pi over 3, and so on for the red region. So that builds up a fractal structure, and along these interfaces, you have an infinitely rough transition where with some self-similarity at all scales, etc. So it's not surprising, either of these 3 roots are admissible for your problem. Just like either solution with different S-elastic can be admissible, and where the algorithm converges to depend on where you start from. So we kind of run the same experiment for this, comparing the 1,0 and 3,0, and we found some appearance of self-similar structure at different scales, which suggests some kind of a fractal, but it's very much expected for Newton method. So let me recap exactly what have we learned, why are we doing this, and where is this going? So this Atkinson idea can be implemented numerically, and does work. It's the only proposal to implement this elastic unitarity, and we've tested it for 2DS matrices, and now we're working to proceed to 4 dimensions. We learned some nice lessons, numerical lessons, and now we can proceed to 4 dimensions. This I've explained to you. There's some stuff on the speed of convergence if you have some sort of technical questions. It would be nice to be able to fill this gray gap, maybe using some Newton method that can deal with singular Jacobians. We've discussed already the relation to usual perturbative expansions. I'm not coming back on this. And one comment maybe, I've only told you about gapped QFTs, but in theory, that separation between massless and between 2 to 2 and 2 to n it also holds true for theories with massless particles. So you could, although Atkinson was interested in QCD, or strong interactions, you could actually wonder, could this work if for theories with massless particles? And a priori, we don't see any reason why. And in particular for gravity, because the high energy behavior, the inelastic behavior seems like it's dominated by black hole productions, and they have some kind of universal behavior. Maybe you can actually probe some, but it's like long-term fantasy here. And in higher dimensions, so yeah, this is going to be more hard. The numerics is going to be much more hard. There's two big points. Firstly, you don't have just S, you have S and T, so it's n squared points instead of n. And in addition, you have in higher D, where you just took a square in 2 dimensions. In higher dimensions, you have an internal phase space integral to perform. It's a lot of integrals. If you take 100 points on your grid, that's already 10 to the 4th integral to perform at each iteration. That's intense. So you got to find some way. So we're currently trying to find some solutions for this. Yeah, I'm going to conclude here. I'm all the time already. So thanks a lot for your attention.
Thank you. Are there any questions?
Is there any constraints if you want your theory to be local and not superluminal and things like those?
Right. So in higher dimensions, we're going to be essentially assuming a Mandelstam representation for the amplitude. So that should, if you ensure elastic unitarity and inelastic unitarity, this plus the causality structure given by the analytic structure of Mandelstam representation, that should take care of that sort of pathologies. For look, I'm not too sure about your question about is the theory necessarily going to be local? I think so, but I may be missing some basic point.
So in 2 dimensions, is there any notion of locality built in here?
So you're asking me about is this set of axioms implying that the theory is local? No. Where is it? I mean, I suppose, wouldn't non-localities introduce some other type of singularities, other branch cuts over and?
I don't think so. I mean, I don't know probably, but I don't think there is any, locality is usually formulated in terms of Green's functions or Whiteman functions or things like those, not in terms of S matrix.
Yeah, I'm not sure. That's a good question. Yeah, I'm not sure how to answer.
Is the fact that there are a finite number of poles related to locality, because some kind of non-locality can be regarded as many modes, many particles, right? So maybe some kind of locality is already imprinted in the fact that there are few poles. But yeah, so
maybe
good question.
Yeah, good. So thanks. It could be, I guess, if you had some kind of accumulation point in the bound states, and you would have a bound state that accumulates towards S equal 4 with oops. those bounds, so if you had bound state that kind of accumulated here and having an infinite, they would correspond to some kind of non-locality of the theory, I suppose. Yes. So in that direction, going in this direction, yes, you're right. Finite bound state. Sorry, non-locality would correspond to this, but I wouldn't know how to make this statement more general. But yeah, that's a very good point. Thanks. We don't allow essential singularities of this sort in the spectrum.
You know, like in the CFT bootstrap, you usually have some kind of kinks, some kind of corners of admissible regions, and usually this is like the best place to focus on. Do you have anything like that here?
Yeah, I mean, in a sense, so in a sense that's kind of even more brutal because it's the complete solution. But this plot I was showing you before, where is it? Yeah, that plot, for instance. So here you have the logarithm of the coupling, and here you have the mass of the bound state. At this black curve are located integrable theories that have just one bound state and no zeros. And that's those that maximize the coupling. So if you want that region here is special, it's inelastic. It's purely elastic amplitudes that have exactly one bound state and no zero. But in 2 dimensions, the problem is kind of, there's not that many parameters to play with. In higher dimensions, any boundary of this space of function, that's completely unknown. And the boundary of that space in higher dimension would be very interesting, I mean, to probe. But of course, we don't have anything to report on yet for this. And actually, it turns out, I think, I mean, I don't know that literature well enough, I suppose, but I think there's some papers using more traditional approach to bootstrap S matrix that have been seeing some kind of kinks and stuff like that for the Bion S matrix. This paper by Penedones and Diarra a few years ago showing kinks, seeing kinks. So there are these things that appear in higher dimensions, but they're not as good, as well understood as they are for the CFT bootstrap.
Thank you.
Yes.
I have another question. I was wondering about this again. Go back to that previous question about the form of the elastic part of the amplitude. That you said that it comes out in that form of square root over square root. If I understood correctly.
Yeah.
You had that as a result.
Yeah.
And
you see this coming out, yeah.
Yeah, and I think so. This form already has this crossing symmetry that you said, which in this case is just reflection around 2m squared. But like in 2 dimensions, do you expect the crossing symmetry to be somehow built in your framework?
Yeah, the way you implement the map, because of that dispersion integral here that contains both cuts, the way you implement the map, you always obtain a result that's crossing symmetric, kind of.
Right, like, yeah. So here everything is one-dimensional, and your integral, your problem is formulated in a cross-symmetric way. But in 2 dimensions...
you meant higher dimensions?
Sorry?
Did you ask for higher dimensions?
Oh, yeah, I meant like in 4 dimensions when you have SNT, and so you have a 2-dimensional problem.
Yeah, right, thanks. Good question. No, it's not here. Yeah, so in higher dimensions, you just you compute the row, you compute the double disk in higher dimensions, row of ST. You get that by a double integral of the single disk. Let me call that IMTN. This is n+1 IMTN. And what you use at the step n+1 is you build row n as row L st plus row L ts plus your function vi, that's explicitly crossing symmetric. From this is the double disk. From this, you compute the single disk imtn given by the integral of rho. Just like you get dispersion relation is that integral of double disk is single disk. Just like you get that the function is the integral of the single disk. So that's how you do it. And your question refers specifically to this step here. You need to sum to enforce crossing symmetry here.
Mm-hmm.
And thanks, it also gave me the chance to present how that works.
Okay, so you enforce it. Good.
Yeah.
Nice.
No, thanks for the question.
Any further questions?
Well, maybe about that that strip of theories that to which you cannot converge at the moment. You just you said that it would be nice to get a way to converge them somehow with some other method.
Yeah.
Is that something doable? Like maybe some what you change to Newton's method that takes into account the first derivative, and you start seeing more. If you take into account the second derivative, maybe you get...
Yeah, it's a really good point. Indeed, when you have the problem on that line, it stops converging on this line, red line, which is new. We don't see anything now. It stops to converge on this red line because the Jacobian becomes singular. So when the first derivative is 0, you could indeed use the second derivative. So you need to compute the Hessian. And that's one approach to solve, to try to go further. Indeed.
But then you're likely again to not get to the very edge.
Yeah, who knows? Maybe that's enough actually. The structure is not, that guy is not a beast. It's just a rather simple function. So maybe we were just unlucky that it stops converging halfway. Maybe with just a bit more, you go all the way.
Okay, that would be interesting.
Yeah.
Because that would make sense if it converges already after the second derivative is taken into account. Then you can expect that your high-dimensional framework is going to also...
Yeah, but in higher dimensions, it's unclear if Newton method is going to be the most efficient because it's extremely costly to compute this Jacobian.
Mm-hmm.
So
okay.
Yeah, we don't exactly know.
So you're thinking about just using the fixed point to start?
That would be the simplest thing to do at the first step. So we're trying to do this. But at the same time, fixed point converges less fast. So maybe 3 iterations of Newton are good enough, and you don't need 20 iterations of fixed point. And maybe that's a better strategy.
Okay. Yeah. Thanks.
Thanks.
Piotr, two questions, if that's okay. One, have you tried converging to using Newton's method to no CDD poles but a few CDD zeros?
So we definitely did. Yes. So that yeah, we did. So if you have, but you need to have some inelasticity, I think. Oh. Otherwise, you will converge to 0.
Oh yeah, of course, with some inelasticity.
So you add some inelasticity, and then yes, you obtain an amplitude that has some zeros.
Oh, okay. I guess the second question.
No, sorry. I withdraw what I said. That wouldn't with Atkins. So that's right. So sorry. Thanks. Good question. So with the fixed points, by having no pole and just inelasticity, you iterate and you find this function without S elastic. You find just this exponential. And we did, to do what you said, we should have tried with Newton, and we didn't do that. So we found that just the exponential without the S elastic. So it had not even a 0.
Mm-hmm. Okay, that makes sense, I guess. For the higher dimensional case, did Atkinson prove that it should converge for any reasonable choice of the inelasticity? Or do you expect to find something like you found here, where there are big regions of convergence, but also big regions of you give a reasonable inelasticity, but you don't get convergence?
Well, yeah, I mean, I suppose you would. So yeah, there's several aspects. Firstly, if it converges at all, we'll be happy because that's already intense enough. But what we observed in that case is that whatever Atkinson proved we found something bigger. We found a bigger space in which it converges, which is a bit of a scheme. Sorry, it's a bit of a, I'm kind of cheating when I'm saying this, but essentially this is the idea. Atkinson was interested in sufficient conditions to have convergence. He didn't try to optimize the bounds so much. And we completely believe that you can go much beyond the bounds of Atkinson. And this is kind of what we observe in 2 dimensions. Actually, in 2 dimensions, it's even worse. The proof that Atkinson did doesn't really even seem to work. So Atkinson may have concluded it shouldn't work in 2D, and experimentally it does just work nicely. Or at least, sorry, let me rephrase that. We haven't been able to find a way to make Atkinson proof work in 2D. And that's kind of related to this CDD ambiguity, we believe. The fact that you have many solutions that correspond to the same problem. And because the fixed point solution is supposed to be unique, if you have many solutions, it's not clear exactly, these 2 statements clash. You cannot have unicity and many solutions at the same time. In 4 dimension, that's not there because you don't have elastic S matrices. So it's one source of problem that goes away. But yeah, we expect it would be very natural to expect that whatever boundary of space we find doing fixed point, it's maybe not the actual boundary of function space. So that's why it was important to do in 2 dimensions, because we saw that the boundary doing fixed point is not the whole space. Then doing Newton, you get something better, but you may be still not there. So if we do fixed point and Newton in 4D, we cannot be completely sure we find the full space of functions.
Yeah.
So very good point. Was that your question?
But for Atkinson, there is he gave some criteria on function space, and you do expect that criteria because he proved it that in principle should work, of course, with the appropriate.
Yeah. So that's something you expect, at least in that range, because it's a mathematical theorem, unless there's some dirty mistake in there, which there's no reason to believe that. We looked at the computations, they look completely correct. In that range of function space, you expect convergence.
Thank you.
Thanks.
There was also some question on the chat.
Sorry, I didn't see any of.
About machine learning algorithm that you mentioned.
Yeah, I asked if it's easy to give like a very brief account of how would it work.
Yes, it's not easy because that's outside of my field of expertise. But I think the idea is that let me still say a few words. The idea is that instead of fitting, the idea of using machine learning here is to use instead of doing discrete approximation or polynomial interpolation, you fit your system with a neural network, which is a function essentially, and the neural network kind of ends up on the correct function by also some sort of iterative procedure. So you fit with your function, and that function is a neural network instead of it being a sum of polynomial. So it's for the approximation scheme. That's pretty much all I can say, because this is pretty much all I know. Thanks for the question. Sorry, you're muted.
Sorry, and are there idiosyncrasy differences, like in the how does the complexity scale with when you go multidimensional versus the one-dimensional case?
A lot. Like like I was saying, the first step is that you have if you wanted to play the same game on a grid, you have a grid of size n squared. And then the problem is now that instead of having a simple square, you have a phase space integral that's a double integral to compute at each of those n squared points. That's a lot. Doing polynomial stuff, you can pre-compute the integrals, but that's a lot as well. So it's not even clear if it's worth it to pre-compute the integrals. It scales a lot, the complexity. So we'll definitely need to do something better than Mathematica, like maybe cluster computing or something. Right now we're doing tests at very low number of points to see how exactly, what's the degree of power, numerical power we need here. Thanks.
Thank you.
But we're hopeful. I mean, it can be made to work.
Okay, good. I don't see any further questions, so thank you very much for a nice talk, and thank you everyone for coming.
Thank you.
And see you next time.
Thank you. Goodbye.
Thank you.